Perhaps you know that we will have a new metro station after a couple of years in the middle of campus, and there has been a competition of artworks to metro station of this west line. And the artist who has worked with the Otaniemi station, hopefully later called Aalto University Station, is Kari Kaveen, and he has made a proposal of a work consisting of 5 platonic solids: tetrahedry, octahedry, hexahedry, hedron, dodecahedron, and an icosahedron. And the name of the work is something like "The one who don't know geometry should not work here." And this metro station is the gate for this campus, so to go forward, no one who don't know geometry should not come to Otaniemi. Perhaps George Hart, I'm pleased to introduce, will explain us why. And his famous and inspiring mathematic sculpture or designer, should I say, and he also arranged inspiring lectures and workshops. Perhaps some of you were involved in workshop in Design Factory within a couple of days. I had a possibility to see some of that work yesterday afternoon, and this space was really full of passion and inspiring atmosphere. And I just show some images of the work you and your student made, and I was thinking this Kaveen's work, how we could understand this work and take it part of our community. Please, George, and tell more about your work.
Okay. Oh, this I turn off.
Okay.
Thank you. My microphone is on. You can hear me? Yes. So thank you so much for inviting me here. I'm having a wonderful time in Finland. I apologize, I cannot speak your language. I can only speak English. But all the people I have met, we all speak geometry. It seems that everyone appreciates the mathematical ideas of art that I'm trying to show. So what I have here spinning is a computer model of a design which I thought of a couple of months ago, and I made a little paper model of it and decided when coming here that we should make a big model in wood. And then in fact we made 2 big models, but the size you see on the screen is almost the right size. It is about 2 meters in diameter. There were 2 of these. And this we built yesterday afternoon in a workshop with students. So if you go over to the Design Factory, you'll be able to see those. And this morning I did a different workshop where we made a mathematical model which is hanging outside, which you should take a look at. And let me see if I could find it for you. It relates to something like this. This is called the 120 cell. It's an object which lives in 4 dimensions, not 3 dimensions or 2, but 4 dimensions. And geometers study mathematics in many different sorts of spaces, including higher dimensional space. And it's a beautiful object in 4 dimensions. I can't really show it to you. What you're seeing is a kind of a 3-dimensional shadow of this 4-dimensional object. So you lose a lot of information, but still this is a beautiful shadow. But by making the shadow, it helps your mind learn and think about the 4-dimensional object. So what's outside hanging, you'll see it when you walk out the door, is sort of a cousin or a big brother to this, what's called an expanded 120 cell. And a number of students worked with me today to create this, and it uses almost 5,000 pieces of plastic that fit together. So take a look at that. But what I'm going to show you here, most of my talk today, is something about my sculpture. This is good. So I like to create mathematical sculptures which take ideas that I find interesting as a mathematician. Mathematicians are trained to learn about what are beautiful structures, what are things in the world of ideas that are just an elegant proof, a beautiful way of thinking about form and structure and pattern, and to work with those in your mind. But I like to take these ideas and find a way to make them physical so other people can understand that mathematics is really about beauty. Mathematicians are busy thinking about beautiful things all the time. So this is a sculpture which is made of CDs. You can see how they glue together. It's actually based on a form which is used in English. We call it a soccer ball. You might call it a football in Europe. And it's also the form that carbon-60 forms. And it's a beautiful geometric shape. And I thought about different ways of making it, and I just ended up with this way that uses CDs glued together with a little bit of a bend. But then once you build it, it's maybe almost a meter in diameter. When you build it, it has beautiful reflections and beautiful sense of structure to it. And I always like that, creating something which is beautiful. This is another Seedy sculpture. This one is at UC Berkeley in California, in the computer science building there. This one is maybe 2 meters in diameter. And again, it starts with an idea. The idea in this case had to do with a shape which is made of kite shape and triangles. And I thought it was a beautiful shape for different mathematical reasons. Maybe I can draw on this. You see my mouse here. So there is a kite here, for example. And the kite, because it is a kite, has a reflection line. So it has 2 equal angles. It has one angle and another angle that are equal because it's a reflection. But this kite, not just 2 angles, but has a 3rd angle which is equal. So it has 3 equal angles and one that's not. And I discovered that you can make a form that has these kites with 3 equal angles, and it seemed too much of a constraint. That it was surprising to me that it's possible to cover the whole sphere with 60 kites and 20 equilateral triangles. And as a mathematician, that's the sort of thing which I find kind of elegant and surprising. And I could write a little mathematical paper, and other mathematicians in the world of geometry would then see what I like and appreciate it. Or I can make a giant sculpture, and then thousands of people can see it. So I like to create a sculpture which is in some sense like a publication of something interesting to me. But it's more like a sculpture. But I try to make a sculpture that when you look at it, there is something you can learn, that the professor in me wants to have an educational purpose behind the scenes in addition to the art. So everything I will show you has a story about the mathematics. But I will not have time to tell you all the stories, but I'll tell you a little. So this one is made of pencils. There are 72 pencils. And if you look at one color goes through like a hexagon tube. And then there's 4 hexagon tubes. They're all hollow. So inside is a hollow space. And if you could have a room of that space, if you were a little mouse, you could live in that room. You would live in a space where the light could shine through in 4 different directions. The shadow of your house would be a hexagon, because you can imagine the sunlight going in the direction of the pencils, and the shadow in that direction is a hexagon. So there's some shape inside that has 4 different hexagons as its shadow. And if you try and think about, is that possible? It turns out there is one shape well known that has 4 hexagon shadows. Do you know this shape? Does anyone know a shape that I can hold and shine a light on it, and 4 different ways the shadow would be a hexagon? Someone must know this shape. Maybe that was the answer in Finnish, but yes. So, oh, you're way ahead of me, yeah. So the rhombic dodecahedron is the hard answer. The first easy answer is a cube. It turns out if you take an ordinary cube and shine a light in the direction of a diagonal, the shadow would be a hexagon, and there's 4 different long diagonals. And that's surprising. But that's sort of well known among people who love geometry, that the hexagon, that a cube has that property. But then I find another shape, or not, I didn't find it, but there is another shape, a rhombic dodecahedron, which is more complex, but it's a beautiful shape. And I wanted to do something, a sculpture of some sort with that shape. So here, the pencils go along the edges, and inside there is a room you could live in the shape of a rhombic dodecahedron. It's a very important shape if you're a crystallographer, if you're studying materials. There's many places where this shape comes up. So this is a sculpture which in some sense celebrates that shape in a way that gets people to think about it. There's also a color aspect here. I chose 4 pencils In English, we say CMYK for printing, cyan, magenta, yellow, and black. So these are exactly the CMYK colors. So you can stand in different places, and depending on where you stand, you see more of one color or more of another color. So the color changes to different colors within the CMYK space, depending on where you stand. So I always try and combine sort of a mathematical story and an art story, and also an engineering story. How do you put these together? How do we build these things? In this case, there's tiny little dots of glue that I put in with a little brush between the pencils so you don't see it, that hold it from falling apart. So for any sculpture I show you, you can ask me 3 questions: the art question, the math question, or the engineering question. How do you build it? This one is like a mosaic. I start with a fiberglass sphere, and then there are 902 pieces of wood in 13 different shapes, and I have to find out where to place them on the sphere to build the whole shape. And then there's interesting paths. There's a branch of mathematics called graph theory that deals with how things connect to each other. You just imagine diagrams of dots and lines. And it turns out that if you make a dot for each triangle, dark triangle, and you connect the lines to each other, there are 6 different worlds. I can't go from one to the other by a straight line unless I turn. But if I put a dot for each yellow hexagon and see how they connect to each other with yellow roads that are straight, then it becomes one connected world. I can go from one place to another through some intermediate hops. So there's a story about graph theory that underlies this particular sculpture. This one has to do with colors and a branch of mathematics called combinatorics, how to combine things. There are 5 different colors. If you look at any one piece, it crosses 4 other pieces in the other 4 colors. So each piece touches 4 pieces, but they never touch the same color. They touch 4 different colors. And they wind around each opening that's 5-sided. You'll see each of the 5 colors. So it took some mathematical combinatoric thinking to find out a way to assign the colors to make that particular pattern. Here's a sculpture that I did at a library in New York in the year 1999, at the turn of the year 2000, as a celebration of the millennium. And I asked the people in the library to vote for their favorite library books, and I used a computer-controlled carver to carve the titles, and I gold leafed them. And I brought all these books to the library. Each one is hollow wood with a steel rod through it. And the donuts are cast in bronze, and I drilled some holes, so the pieces slide together. And so at the library, we had a kind of a party to put together the sculpture and make this large ball, which celebrates the best books of the century as voted by that particular library. And to me, what's important is the geometry. The way the sculpture goes together, each donut has a hole in it. If everything was finished except for one book, I could not put the last book in because both ends would have to go into place that would be fixed because there's steel rods holding it. So you cannot do it all one at a time and expect to put in the last one. So instead, I had to think of a different way to put this together. And this is a particular kind of shape. It's called a zonahedron. And a zonahedron is a shape which mathematicians study where all the edges come in parallel families. So from one edge, there is a parallel edge and a parallel edge. And you can follow around a series of edges that all point in the same direction. Because each face is a parallelogram. So for any edge, there's an opposite face. So if you work with all parallelograms, then all the edges come in parts. So I can take it apart in half. And one half will be parallel to the other, so I can, as the last step, join 2 halves together. And then each of the halves can come apart on different parallel edges. So the idea of building this and coming together with halves joining in parallel lines is possible because it's not just any shape. It's not an icosahedron or dodecahedron or whatever. It's a zonahedron, and a zonahedron has that special mathematical property. So I have too many sculptures here to tell you a story about all of them unless we stay all afternoon. So some I'll just show you, and you can think about what may be happening. But some of these I use a laser cutter for cutting. So I like to use computer technology as much as possible to do the things that a computer is good at. So here there are 180 pieces of wood, and each is curved in an interesting way, and they have a mortise and tenon joint. So one goes through another, and then a pin, a little wedge pin, locks it together. This is at a university in Spain. And that one, what you saw in wood, was 1 meter. Then I made another one larger, 2 meters. This is aluminum, also laser cut. But what might be surprising to you, what you won't see unless I explain, when you look at the shape, you see many different angles and curves. But what I see, because I designed it, I see a right angle, 90 degrees, everywhere. It turns out, the way the laser cutter works, the laser can cut straight into a piece of metal, and then it makes a hole which goes straight through, not at a tilt. Lasers don't usually tilt. So when I put two pieces together, if I make the joint at right angles, they will fit tight. If I had to put it in at an angle, it would be a little bit sloppy. So I thought to myself, what shape can I make that has as many right angles as possible? Wherever two pieces touch, I'd like them to touch at 90 degrees. So for example, a cube would work. I could make a cube, and wherever two pieces touch, they touch at 90 degrees. But in fact, here, wherever two pieces touch, they join at 90 degrees. It's hard to believe when you look at this. You can't see it unless you help me build it. But there are 180 pieces, and each one touches several other pieces, but every connection is at right angles. Here's a piece where what I'm trying to study is how to get things to hold together without connectors. So as you've seen, most of my work is constructive. I start with pieces and I put them together. So I spend a lot of time thinking, how do I hold the pieces together? Should I use glue? Should I use screws? Should I add a clamp? Whatever. In this case, there is nothing else that connects. It's not glued. There's no welding or brazing or anything. Each piece, you see the shape, has 6 little notches. 3 near the middle face one way, and 3 near the outside face the other way. And they lock together, and it's designed so that I just put the pieces together. The very last one I have to bend a little bit, force it in, but then it springs together, and no piece can move. They cannot spin left because some of the notches go left. They cannot spin right because some of the notches go to the right. So the whole thing holds itself together very, very strong, and it cannot fall apart, even though there is no connector. It's just the material itself. And then this gives me a kind of a challenge. As a mathematician, I like to solve problems. This is what mathematicians do. They think about a hard new problem, and they study ways to solve it. So the problem for me was to come up with an interesting design which is attractive as a sculpture, visually engaging to look at, where I could use this technique to make none of the pieces need a screw, that everything just fits into place. So I have several sculptures. This is the same idea, but more complex. Again, the pieces just spring into place, but much more challenging. It took me many hours to get this because the pieces go through each other in a complex way. This is similar. This was actually a retirement present for a friend of mine, but it's a puzzle. There are 30 long pieces, and they go together, and I gave it to him as a puzzle. And he has not yet taken it apart. He was scared that he will never put it back together. But it does unsnap and reassemble. This is a sculpture I did at MIT. I was artist in residence there 5 or more years ago. Laser cutting pieces that then screw together. This one is maybe 1 meter in diameter. This is sort of an homage to M.C. Escher, you know, the Dutch graphic artist Escher, who did many works with tessellations and also enjoyed reptiles, chameleons, lizards. So I was trying to do something three-dimensional that has a flavor of Escher, but being a sculpture. And again, this I did like the workshop we had here yesterday, with many students helping me put this together. So again, I should not tell you about all my sculptures. This is a wood version that then I made larger and then made in metal. This is in paper. Again, very, very interesting story about why these fit together and how I get them together. But we do not have all day for too many stories. But I do like paper. I've always enjoyed working with paper. Since I was a child, I would cut out paper and put it together. But as I grow older, I make more complex things. But here there are pieces that look like the number 3, but 2 of them overlap together to make, looks like the number 8. And maybe you cannot see at that distance, but at the very tips, at the ears, there is a little notch, and they slide together. So this holds together without any glue. Everything goes in a complex way and then just holds by friction. It took me, I think, 4 hours of experimenting to figure out how to make it, trying things, and it would fall apart. Because once it's only a little bit assembled, there's nothing to hold the pieces in place, and then it falls. And it's very tricky to know what goes in front and what goes behind when it's only partly there. But after 4 hours, I figured out how to make it. And then after 4 more hours, I finished. I was able to build it. It took 4 hours to assemble using little tweezers. It's a small sculpture. Again, I cannot tell you about everything, so I'll just show you some pictures. If you go to my website, georgehart.com, you could read about more of these sculptures. This is acrylic, plexiglass, perhaps you say, a clear plastic. You can heat this in the oven. It becomes soft, and then form it into a shape, and let it cool, and then have the pieces which then fit together. This is acrylic, but flat, not bent, laser cut. And many interesting math stories. I would like to tell you how these work, but I don't have time. Let me show you some now that are made on a 3D printer. So some of you have worked with a 3D printing device. This is a machine which builds in 3 dimensions for you. So I can think of something, I can, on the computer, create a computer model of it, a digital model, and I can push a print button, and the model goes to this machine. And depending on the type of machine, works in different ways, but some of them work by melting plastic and squirting at a layer at a time. Some work with a powder, and the powder is melted by a laser. The computer-controlled laser will shine on it, melt the powder, and then the powder is in a chamber that goes down a tiny fraction of a millimeter, and more powder comes up, and a little roller gives me maybe 1/10 of a millimeter of new powder. The laser melts that, and that goes down, more on top. So a layer at a time, we build up my object. And then at the end, I take away, I vacuum away the loose powder that wasn't melted, and I have my object. So this was made like that. The technology is called selective laser sintering, and it allows you to make very complex, very interesting shapes. This is a kind of a fractal. It's an icosahedron of icosahedra of smaller parts, and it's something which I could not make myself. So I like to work with my hands and to make things in metal and wood and CDs and pencils, as you see. But some ideas are too complex. But for this idea, I can send it to the machine, and the machine can make it. So I like the fact that the idea is not just trapped in my head, that other people get to see it. So I'll show you a number of sculptures made on a 3D printer. Here the story has to do with hyperbolic space. So mathematicians study different kinds of geometries that have different rules than the Euclidean geometry that most people study. And in hyperbolic space, there are many, many wonderful things. If you've never studied hyperbolic space, you should read about it and learn. And in particular, say, if we look at the ceiling here, you see 4 squares meet at a corner. Tiles that are squares, you can put 4 together. In hyperbolic space, there is more room. So I could put 5 squares together at every corner, and that makes sense. And the rules are consistent once you understand it, and do many, many other wonderful things. So I like to take ideas from hyperbolic space and translate them into our space, but it requires some distortion, some adjusting, because it's a different kind of space. So this is actually a space where a pattern where the holes look like they get smaller near the edges, but they're really the same size in hyperbolic space. But I design it there, and then I bring it here, and it becomes distorted in certain ways, but it still shows patterns that are only possible in hyperbolic space. It's a long story to describe, but I want you to understand that there is something mathematical here. At the same time, there is an artistic idea. I want to create something that feels organic. I wanted something that felt like maybe it could be a creature. Maybe under the ocean, there could be something that looks something like that, and yet having a mathematical pattern. And this is similar in the same idea. Again, it's based on what a mathematician calls a uniform tessellation in the hyperbolic plane mapped through the Poincare disk into a 5-2 torus knot. That would be one possible way to describe it. But what it really is, it's a sculpture in which I want you to understand that mathematics is a beautiful subject. Similarly, here maybe you can perhaps see what I'm saying. If I look at a corner right here, say one corner, I see 4 sides, 5 sides, 4 sides, 5 sides. This corner has 4, 5, 4, 5. In fact, every corner has 4, 5, 4, 5. So here I see 4, 5, 4, 5. It's like the tile on the ceiling where you have 4, 4, 4, 4, except here I can have pentagons and squares. And in hyperbolic space, those are regular squares and regular pentagons, and they fit nicely. But I have to distort them slightly to turn them into the sculpture. But it comes out to be a nice 3-dimensional shape. So each of these sculptures has its own story. I will not say them all, but I will say with 3D printers, I can take many ideas and bring them to reality and include color. So some of my sculptures I color myself, I paint. This is made on a 3D printer which knows about color. So on the computer, I can choose an algorithm for what color I want every single dot to be, and then the machine builds in color. Here you can't see the inside. The inside is the interesting part of the sculpture, but there's many small details like a flower inside. Here you can see the inside better. I have yellow color and red color, and as you go in, the pieces get smaller and smaller because this material is something like plaster. If I dropped it on the table, it would crack. But if I just hold it gently, it is quite strong. So I made the very delicate parts near the inside and the outside strong for holding it. And again, there's a mathematical kind of architectural story about what is that shape, how do these curves work. This is in fact entirely made from pieces of spheres. Every curve that you see is carved from a surface of a sphere with different sized spheres. This is modeled more on a kind of a plant form. I was thinking of a seed of a tree for the inside and a kind of a flower-like growth on the outside. Here I'm thinking of something that might live under the ocean, related to starfish, but more complex. Again, there's a kind of an organic feeling to it, but there's also a mathematical story. You may see the shape of an icosahedron here in the outer form. So again, each of these I could tell you about, but I'll just let you look. Oh, I should mention, if I go back to this one, I have a postcard here that shows this one. And at the very back of the center aisle, you see on a table, there's a pile of postcards. You're welcome to take a postcard. It just says, go to georgehart.com to see more. Here's one which is made in just one color. This is made of little tiny pieces like chainmail, chain. There are thousands of little links. And what I did is I made a ball out of chain, and I have to design each piece of chain and then send it to the 3D printer. The 3D printer prints the entire thing. What you may not see is that the chain is partly flexible and partly solid. Here's a close-up. You can see each little piece was made separately. And the picture here on the right, the blue part, I made the chain pieces big enough so that they fuse to each other. They cannot move. The red part, I made the chain fine enough so it can move. So the blue keeps the overall structure of a dodecahedron. And inside each red area, the chain is free to move, so that gravity lets the bottom hang down. So as you see on the left, the top part, the chain is hanging. The bottom part, it makes a sphere. But no matter how you turn it, it looks the same. The chain which is loose on top will hang down. The chain on the bottom makes a hemisphere. Here's a sculpture which I made at a university in America 2-3 years ago. This has 9 pieces. Each is laser cut. And this tells the story of a mathematical proof. So in your math classes, you study that we can begin with sort of an axiom, a certain beginning, and say, from this, I conclude this, and from that, I conclude this. And we have a series of conclusions until we end up with a theorem. We have a proof of something wonderful. This sculpture tries to illustrate that idea. In the very back is a yellow structure, which is a simple structure. And then the next one over is a little bit more orange. And I change the structure slightly. I move one piece next to another piece. As you go to each sculpture from one to the next, the color becomes more towards red. The structure changes just a little bit. I add some holes, it gets bigger. By the time you get to the very last structure, I have something which is new and surprising, but it follows in a step-by-step pattern. You can see how I derive it if you walk across the room from one end to the other. Each of these is about 4 feet, 1.3 meters in diameter, made of steel. So I show you here how we built it. I designed the pieces, I laser cut them, and I had them powder coated in different colors. And I announced to the university we were having a sculpture barn raising. Come help me build a sculpture. And hundreds of people came during the day at different times. And I gave them instructions on which pieces connects to which in what order. And so we overall built all these and then hung them up. Here's another sculpture barn raising I've done. This is a model done on a 3D printer, which is small, of the design, which I made first. And then each of the pieces, you can see little triangles. Some of the triangles are flat, and some of the triangles are bent. I made all those parts and brought them. This was outside the Smithsonian in Washington, D.C., on the mall in Washington, D.C. And I invited the public to come help me build the sculpture. And you can see that they screw together, and we start by joining particular pieces in a particular pattern, and we build up larger units and larger units. It begins to grow until at the end of 3 days, a little each for 3 days, we have a big sculpture which is more than 1 meter across. And again, there's a very interesting story about the triangles and how they fit together, and the parallel ones have the same color. So this happens to be that sculpture at Towson University near Baltimore in Maryland. And that happened to be the site of a conference called the Bridges Conference. So if you like the kinds of things I'm showing that combine mathematics and art, you would like the Bridges Conference. So my sculpture here was used at Bridges as sort of the logo for this conference last year. But the conference moves around to a different university each year. This summer, the last week of July, the Bridges Conference will be not too far from here in the Netherlands, in Enschede. So if you're interested in connections between math and art, you will find hundreds of people coming from around the world who do painting and watercolor and quilts and beading and dance and music in any way that combines mathematics and art, and much sculpture, a lot of sculpture. So there's also a postcard about that. If you're interested, pick up the postcard, which is at the end of this aisle near the door as you go out. And it tells you about the website that you can learn about this conference. And I thought as long as I'm giving a commercial, I would give you also a commercial for this Journal of Mathematics and the Arts. If you're a professor, an academic, and you do original creative work in math and art, and you want to publish it in a journal, this is the right journal. I happen to be the editor for sculpture, but it deals with all the different arts and connections to mathematics. And I don't know if your library here has it, but if you don't, you should have the library subscribe to it and read all the articles. It's a wonderful journal full of surprising, beautiful things. Oh, I have one more commercial, as long as I'm doing commercials. So this is a sculpture I made called Frabjus. And sometimes people say, I love your sculpture, I wish I could have it, but there's only one, I don't like to repeat. So this is a sculpture that I actually made, which is commercialized. So you can buy this kit. If you just go Google for Frabjus, you'll find places that you can order it. And there's a simple version in blue or a fancy version with iridescent color. And I did that as an object partly to support the Museum of Math. So let me give now a commercial for MoMath, Museum of Mathematics. This is a museum in New York City. It just opened this past December, 4 months ago. And it's right in the middle of New York City near 5th Avenue, 26th Street. And it's full of fun, hands-on, cool things that you can make. I spent most of the last 5 years designing this museum, founding the museum, and creating exhibits for it. And you should just go and see it if you're in New York. I also mentioned that if you're there the first Wednesday of each month, there's a free lecture on mathematics. But here's a typical exhibit. This is a square-wheeled tricycle. So each tricycle has 3 square wheels, but as you ride, the ride is smooth. You don't have bumps because the floor has the bumps that compensate for the corners. So when the corner of the square is in the bottom, and you can solve a mathematical equation to find out what shape is the bump that compensates for the square wheel. In fact, for any shape wheel, when you tell me what shape wheel it is, I can tell you what shape floor will cause the wheel to have the center stay smooth. And because the center is smooth, then the tricycle, which rides on the center of each wheel, has a smooth ride. So there's 2 of them. One goes one way, one goes the other way. But we have 6 different size squares. As each wheel is further out in the circle, you need a larger size wheel. Here's an activity at the museum where you can build this object. The pieces have little connectors on the arms, and it screws together. And you can think about different coloring patterns. There's many different ways to apply the colors to the pattern here. So here's just an example of a kind of a workshop that I did when a class comes to the museum that they can build things. So I like building things, as you may have noticed. I wrote a column for Make magazine for 2 years that shows you different things you can build. So you can look online and see this, but I'll show you a few. So one thing you can do, and I recommend you, if you have a bagel here, or a donut, but a food in the shape of a bagel, there's a way to cut it into 2 pieces that are not just 2 circles, but are 2 linked circles. So if you cut on this line, the 2 halves of your bagel are linked together. So this will be your homework, I recommend. If you, next time you see a bagel, cut it, find out how to cut it into two pieces. They're equal, congruent pieces, but not separate. They're linked. Here's an activity I designed using laser cut pieces that snap together and make a building kit, and you can build large things that have tetrahedra and octahedra. And anyone with a laser cutter can copy this and build fun things. Here's a kind of a challenge. You know about a ship in a bottle. This is like that, but it's an octahedron in a balloon. So the octahedron is made of rubber, and it's inside a balloon. And the challenge for you would be, how can you repeat that? How can you create your own octahedron or other shape inside of a balloon? This is made of light sticks. So each stick has a little battery and LED in it, and people wave these around at a concert or whatever. But I found a way to connect them with rubber bands and to make large structures. This is with CDs. So taking CDs and overlapping them and using a cable tie to connect them together, we can make big structures. These are shish kebab, bamboo skewers for cooking food, and little rubber bands to make a shape a mathematician calls a hyperboloid, which is the shape you may see in like a cooling tower in a power plant. And here's a large one. So I took 2 rings of wood, and this was sort of practice for the Museum of Mathematics, where now there's a big one that you can walk inside of. I just wanted to see how it would look. This is made of Zoom tool. So when you walked in, you saw outside the Zoom tool construction. I've done many large Zoom tool constructions. This one is in Central Park. So in the middle of New York City, I brought, in this case, I think 8,000 pieces, and had 50 people come and help me build this, and we just put it on display out in the ground so everyone who walked by could see this and think about the beauty of mathematics. And we would get many funny questions. People from other countries would come by and say, "What is that?" And we would say, "Oh, in America, we always make this in the park." But we don't always make this in the park. So I also like to make things on a 3D printer. So on campus, you have several, but you may be aware that there are now 3D printers that you can buy in the price of 500 to 1,000 euros, so that you can use these in the home. And people who are interested can buy this, maybe this big, and build their own objects. So this is a machine I have at home, and it melts plastic and squirts it out under computer control. And here I'm just making a little tetrahedron. This was the very first thing I made when I got it. But here you can see a dodecahedron. Here you can see I made pieces that then come together. It's a puzzle. Here's a more complex puzzle. But these home 3D printers are a wonderful way to make fascinating shapes. This is a classic puzzle of thinking of a shape that can fit snugly through a square or a circle or a triangle. There is a shape that does that. And here you can see the shape. It's a kind of a wedge with a circle on the bottom. So I made the file. And once I create the file and put it on my web page, anyone around the world who has a 3D printer can load the file and build it. And so this is wonderful as a sculptor. As an artist, you always want people to see your work. You want to create things and have people appreciate it. So I design all these things, and the file that you need for the 3D printer is on my website. You can download it for free, hit print, and have your own copy. This is a knob for a light dimmer. I don't know if you have the same kind of knob, but in America, often there is a knob in the wall for dim versus bright. And if you lose the knob, you can go to the hardware store and buy a new one. Or if you have a 3D printer, you can just make your own. So I designed a knob that has a particular mathematical pattern. Again, this is based on a hyperbolic tiling in hyperbolic space. But the inside fits over the piece in the wall so that I could replace the knob I lost with this one. And other people all around the world can also have a hyperbolic light knob. I like making things with cards. So these are made of ideas for playing cards, and I have instructions how you cut slots in the cards and put them together. Here's a different one. Here's an example of another one. Okay, so in my time that's left, I'd like to show you some videos. I make many videos. My daughter started making videos, and she sort of taught me that there's a big audience for videos. If you put something in a video form, many people around the world on YouTube will be curious and see what it is. So I make 2 kinds of videos. Some of the videos I make are for YouTube, and these are short videos of different things. I also make a series of videos for the Simon Foundation, and those I make are a little bit more in depth, a little bit at a more advanced level, but still any person might enjoy them. So I'm going to stop this presentation and click on videos. Oh, maybe I have one here. Yes, okay. So I'll show you a piece of this. This is the computer design that, as I showed you earlier, spinning on the screen, of the large wooden sculptures that we made 2 of that you can go see over in the design factory. But this is a video that shows how I first made it out of paper. So here's the template. There are 60 pieces of the same shape. In paper, I made them with slots, so they just slide together. That was strong enough for paper. For wood, it's a different way to connect them. And then I can lay out on a page a series of these and use a cutter to automatically cut them. So this is a cutter I have that automatically cuts paper. So instead of using scissors, which would take me a long time, I can let this machine cut out the paper, and then I get these pieces, and I use them to put it together. And then the pieces slide together. Here you can see some of them. And it takes 60 pieces to make this design. Because it's paper, I use a little dot of glue to hold it so it doesn't fall apart. And then they begin to snap together, and we make these modules, and then these join more and more together until we have the complete shape. And it's very tricky, very confusing. A few of you I recognize were in the workshop I did yesterday, where we made this of wood. And when you start building, it's very hard to understand the overall structure. As it begins to take shape, it becomes easier to understand. It's very tricky in the middle, but then in the end, there we have the final shape. So if you want to make your own copy, you can go to my video, you can see the template, cut it out, and assemble it together with this sort of instructions. I'll show you a couple of other short videos. Where's the one I'm looking for? So here's the sculpture which I showed you at, this is at Albion College in Michigan. And here you can see several hours compressed into how people are building these metal pieces, screwing together, many hundreds of nuts and bolts and washers to get everything right. And I'm running around very fast from table to table to check that there are no mistakes. And then each one has 3 hooks in it for connecting to a chain. And then you can see the building people came to lift up each piece and put it into position. So the entire sculpture was built and installed in maybe 4 or 5 hours. But recently I've been working with cardboard. So this is a construction I did at the Bridges Conference last year. Everybody says to me, I would like to have a big metal sculpture, but then they say, oh, but we don't have any money to pay for it. So I try to think of how to make people happy, and it occurs to me that I can design things that you build out of cardboard, which look like a big metal sculpture from a distance, but are less expensive. So here is a design which just uses a cardboard rectangle with some slots and a fold. So I first had people build out of playing cards to understand the shape, to slide it together. And then we put the cardboard together, and it just slides. There's no glue or any tape needed. It takes a little bit of a fold to slide things together, and then you unfold to make a lock on the inside. Again, I'm interested in many things about the mathematics here, in particular the color. So there are 5 colors of rectangle. Each rectangle has 4 slots and touches the other 4 colors. So each one never touches its own color, it touches 4 different colors. It takes a little bit of a bend to get the last piece in, but then it locks together and it becomes very rigid. So that's hanging up somewhere at Towson University. So that one only has 30 pieces. I've since gotten more ambitious. I'll show you parts of this video. So here was a design. This has 60 pieces. I will actually step back a little bit. So here I brought a scroll saw to the workshop, and we worked with cardboard, and I have a template, and the students could trace the cardboard together, trace the pattern to the cardboard, and then we cut out the cardboard using the saw. We actually are holding together, I think, 5 pieces of cardboard at once using a big clip. So there's a black clip that holds together a stack. We trace it onto the top one, cut through a whole pile at once until we have enough pieces. And this whole construction took, I think, 3 hours from nothing to the final assembly. And then they start to go together. And here again, I'm using slots. For cardboard, the slots work pretty well to join parts together. And I'll skip ahead because there's a lot more work here to put the pieces together. It grows and it grows. Some more near the end. So I brought a paper model to show people again. And now I'll show you the last 10 seconds of it finishing. And maybe I'll show you one more. Let me see. So this is one from more than 10 years ago. I had a different haircut. You won't recognize me. Believe it or not, that's me. More than 10 years ago. This is a Seedy sculpture at UC Berkeley, California. And I designed the sculpture and cut slots in the CDs in my studio in New York and shipped all the CDs in a little box, small box this big, to California and then built it. There's a structure with fiberglass rods and stainless steel wire which carries the weight. The CDs are not strong enough to keep their shape. So these little wires can hold the CDs, and one chain in the middle allows the sculpture to turn. And this is built in an atrium. It starts on the 6th floor and goes up to the 8th floor. So it's 3 stories tall. And I had to take all the pieces up and build it in place. So it's very high. So on the first day, I made many modules that then joined together. On the second day, I put them together. So first, put a cable there and connect this, and then bring up the modules 1 or 2 at a time to connect onto the wires that are hanging, the stainless steel wires. And I was very afraid that I would drop some pieces on the floor and then they would land and crack, because I only had a certain number of pieces with me, because I needed at my studio to cut with a saw and a jig to get exactly the right angles. But I did not drop any. I was very careful. But each piece has a particular place and a particular wire for which it goes. So I had practiced this back in New York, and so I knew where they went. Here I'm using a solvent cement. So it's a glue that dissolves the plastic and then evaporates. So the plastic is welded together, becomes one piece. And over a couple of hours, it gradually took shape, getting larger and larger. And maybe here you can see better the kite shape and the triangle shape. It's entirely made of these kites and triangles. And there's a bottom centerpiece hung by a wire, and this, I think, is the very last piece. And then part of the way that they hung it that I like there is there are lights coming at it from different sides. and there are light dimmers. So whoever walks into the room can adjust the light dimmers and create bigger shadows or smaller shadows and more or less reflections. This video is before we aimed the spotlights on it. But it gives you a sense. I think you can see a little bit of the reflections on the wall on the right and the types of shadows that you have from the different lights. And maybe one last one, just to give you, again, a sense that I like many different materials and many different things. Let me see. This one, I'm just going to show you the last, the beginning part. So this is the light stick structure. It's hard to visualize, but there's, it's based on a dodecahedron. I'm just going to skip to the end. You can see me standing in there. Just give you a sense of how big it is. But this is the kind of thing that you can make that does not require a great deal of money or time. It just requires understanding geometry, thinking of structure, and figuring out how to put units together. Okay, so I think in order to have time for questions, I should stop here, and I'll be happy to listen to any questions you have. I have many, many more things I could show you, but you can get the same idea by going to my webpage and seeing more things there. So, can I answer questions? Yes?
I'm from Finland Science Education Center.
Oh, wait, I'm sorry. I have to ask you to use a microphone. I apologize.
So can you hear me now?
Yes, very well.
I'm from Finland's Science Education Center, and I'm interested in learning. Would you have any encouragement to students who are not really happy about math? How would you make them, what would you tell them to make them feel that math is really something awesome?
Well, everything I do, that's sort of my mission in life, is to get people to understand that math is really something awesome. I like the way you put that. So the way mathematics is taught in the public schools, people only see certain parts of math. They see some arithmetic, and they see some algebra, a little geometry, and maybe some trigonometry or calculus, whatever. Math is so much richer. Math involves so many wonderful subjects, from group theory and graph theory and combinatorics and probability and discrete math. There's so much more to it. I try and show people that maybe there's more to math than what the teacher has time to show, and to get people to see that math is creative. Most people in math class, they only see, add these numbers or do this division and right answer or wrong answer. They don't realize that what real mathematicians do is a very creative subject. Mathematicians are creating new things all the time, just like an artist is. They think of a theorem that they want to prove, or they think of some result that they want to create a structure. And school doesn't have time, or it's not focused on explaining that math is beautiful, so people don't see that. So I hope that I can get students to see that maybe there is a creative side, maybe there is something more to it. In the end, to be good at math, you have to spend a lot of time. You have to work hard, you have to study it. Making a model or a structure does not teach you everything you need to know about calculus. But if it can get you to realize that math is worthwhile, it'll perhaps give you the incentive to spend the time to do that work. So I hope I'm communicating something of that sort. And I work with teachers and students at all different levels, trying to get people to spread this joy of mathematicians. Because real mathematicians really love math, but they're not good at explaining that to the public. So that's what I'm trying to do.
Cool. Thanks. Do you have a favorite shape?
Do I have a favorite shape? The rhombic tricontahedron.
You'll have to write that up for me.
Okay.
Any other questions? Comments?
Yes.
My name is Markus Valkava from Aalto-University. Although my question has nothing to do with the science, more about your pieces of art as museum objects. as objects in the museum, for instance, or in a lobby somewhere. How do they last time? You saw the video. That was an old object with the Seedys. When they get dusted and so forth, the objects made from cardboard. After 10 years, how do they look like?
Right, so that's a good question. As an artist, you know, life is short, art is long. You would like your art to live forever into the indefinite future. So far, almost all my sculptures are where I left them. I've had one that was damaged, but the Seedy sculpture I just showed you after, I think that was 1997, so that would be 16 years if I can subtract. That one is still there, doing fine. The cardboard structures I don't think of as a permanent sculpture. As I said, that was a way to compromise, to let students have an activity to make something big, but to do it on a budget. You can buy that cardboard for $50 and create something exciting. And yet, I've only started doing the big cardboard sculptures in the last year. I did it was one day I said, oh, cardboard, I just never thought of it. And then once I thought of it, I've been doing a bunch. So far, all the cardboard structures I've shown you and others I didn't show you are still there. They're still fine. So if no one jumps on them, if they don't get wet, they can last a long time. I don't think they're going to last more than 10 years. I wouldn't expect that. But long enough that the students who do it can proudly show it to the rest of the community and feel like, here's a wonderful thing that I made. In the end, I suspect, eventually all of my sculpture will be gone at some point. Maybe the internet will allow things to carry on. But to me, the actual object is important, and I do like when people take care of them, but much more important is that the spirit of creating something can live on in the people who are participating, and hopefully some of them will be excited enough to pass that on to future generations.
Okay, any other questions? I would like to ask you, what inspires you to start a new work? Is it mathematics or some phenomena? Or other question related that you are working a lot with different kind of people of different ages. Is there sometimes question why or could we do this differently? Is it very discipline-based idea you bring them, or is it creative process of perhaps changing idea?
That's a good question. So it's difficult to come to a group in a couple of days and say, let's design a sculpture like this. There's too much you have to know. So for the sculptures that I've showed you, that I work with people, usually I design it ahead of time and I come with a plan, but always the plan changes. So while working here, in making the wooden sculpture that we made, I had a plan, maybe do this step, this step, this step, but along the way people suggest, oh, why don't we do this, or why don't we do that? And I say, oh yeah, that's a good idea. And so I change my plan and I learn. So by working with different materials and different people, I accumulate inside of myself the best ideas of all the different people who I work with, which is great. And to the first question about what inspires me, usually I start with the mathematics. At heart, inside of me, I'm a mathematician, and I feel that math is beautiful, and I'm trying to express that. So each of my sculptures usually begins with a mathematical idea where there's something I say, isn't that neat? And when mathematicians sit together around the lunch table and they talk to each other, they say, oh, here's this really neat thing, and they show each other. And those things would never go beyond the world of mathematicians to the public unless somebody makes them popular. So there are writers, so maybe you know the works of, say, Martin Gardner, who wrote many wonderful books on mathematics and English over the last 50 years. So he wrote great books that show you why math is beautiful. And there are people who work in art, there are people who make TV shows. Just for me, what is natural is to make sculpture. It's just something where I feel I have a kind of a talent that I can bring out. But there's many, many other wonderful parts of math that I'm not showing you that other people can. So you should be looking all around to find the beauty that's part of mathematics, not just in sculpture, but in many fields.
Okay. There's still 1 minute left.
I think we need more than 1 minute for applause.
Okay.
Thank you very much.